Swayam Prabha. Digital India. Educated India.
Having studied steel making fundamentals and current practices, it is now to see what would be the future steel production technologies. Also, what would be required to sustain the future growth of steel making technologies. In this connection, no doubt the developments in the current practices of BOF and electric arc furnace will also continue. Quality steel production as decided by chemistry and inclusion content would be equally important because of the stringent requirement for the industry. In the next few lectures, we will be studying the following 4 aspects. 1. Emerging steel making technologies, and 2nd, refractory in steel industry, 3rd, clean steel, and 4th, process control and automation. So, as such, first I will be starting emerging trends in steel making. What is the motivation of this emerging trends? The motivation number 1, to develop an ecological balanced technology. What does it mean? An ecological balanced technology means when the reactants enters into a system at 25 degrees Celsius, then the products should be used within the system such that the exit of the product is also at 25 degrees Celsius to the extent it is possible. That means recycling, reuse and recirculation within the system is an important part of ecological balance technology. So, in the future to come, this particular issue will be an important. Current practices, no doubt they are using recycling or recirculating or reusing to some extent, but even then the emissions, the hot gases are still discharged into the surrounding at a very high temperature. So, the basis would be to develop an ecological balance technology to the extent possible. Second motivation is in terms of flexibility, to use varying proportion of feed materials. You must be recalling that BOF steel making, it cannot use scrap more than 30%. You have limitations over there. Electric arc furnace cannot use more than 30% hot metal. So, both the modern steel making processes that we have discussed, they have the limitations. So, what would be required? Depending on the availability and supply of raw material, a process should be there which can make use of any proportion of the charged material. For example, if hot metal is available abundantly, then the process should be able to use hot metal and convert to steel. if scrap is available abundantly and hot metal is in shortage, then scrap should be usable, or varying amounts of DRI, that is directly reduced iron, iron carbide, all should be possible to use. So, what I want to say is that a process would be very much desired where the flexibility in terms of varying proportion of charge could be possible, depending of course on the availability. Third motivation could be, you know that around 40% under Indian condition, around 40% steel is being produced by electric arc furnace, and electric arc furnace is highly electrical energy dependent. The consumption of electricity, no doubt with the modern gadgets, it has come down to a very low value, but still the electrical consumption is high. That means the electrical energy is the principal source of heat in electric arc furnace. Now, recalling that electrical energy is being produced in thermal power plants by combustion of fossil fuel, and hence the emissions that being generated in the power plants, that also will contribute to the emissions by electric arc furnace, in a way that whatever electrical energy we are using in electric arc furnace, in fact that is being derived from combustion of fossil fuel. So, in that sense I mean to say. So, a third motivation could be a process which is not electrical energy dependent, not electrical energy dependent. Having seen these motivations, now the one of the process that is being developed in the last few years is the so called EOF, that is energy optimizing furnace. As the name suggests, this is a furnace which is used to produce steel by optimizing the energy which is being produced due to the chemical reaction when hot metal is converted to steel. That means, in short, an energy optimizing furnace is a furnace cum refining unit which has a provision to inject oxygen or carbon below the melt or oxygen above the melt in order to carry out post combustion of the evolved gases. So, this is what the concept of energy optimizing furnace. Now, I will show this figure shows the schematic representation of an energy optimizing furnace. Now, you know this energy optimizing furnace is a combination of three independent interconnected reactor. So, I write down EOF is a combination of three independent interconnected reactors operating in continuous mode. What are the three independent interconnecting reactor? First is the furnace. First reactor is furnace. Second reactor is stack, or you can also call a preheater for scrap. third reactor is recuperator. Third is the recuperator. Now, design of each reactor and their integration with each other is very important, such that gas exits through the recuperator at a low temperature to the extent possible, and at the same time steel of desired quality is produced. Now, let us see the design of the one by one these reactors. If you see the furnace, say furnace part, it contains melt, it has a provision for injection of carbon or oxygen deep into the bath. Oxygen is also being supplied from top in order to combust the exit gases which contains carbon monoxide. So, in the say design of the furnace, so furnace design, what are important issues? The furnace should have provision for carbon injection, provision for carbon as well as oxygen injection in the melt. You require oxygen injection for refining. Second provision should also be there, provision for oxygen injection to carry post combustion, post combustion. So, these two are the important design aspects, among several design aspects could be there. From the refining point of view, these two are the important issues. So, a proper dimension of the furnace has to be selected, say diameter or the height of the reactor has to be selected, so that these functions could be accommodated. Now, if we see the second reactor, which is the stack, this is on top of the furnace. It is connected, joined, so that no waste gases leak. This is an important engineering aspect of this EOF furnace. Now, this stack has to be designed such that the scrap is preheated by the waste gases which are discharged from the furnace. So, in the diagram you see that the waste gases are flowing upward, they are heating the scrap in the stack, and the used gas is passing in the recuperator. So, as regard the stack is concerned, what are the important things? For the stack design, the stack design is important. It is used to preheat the scrap, by the waste gases which is flowing upward from the furnace. Now, since preheating of the scrap is done by the flowing gas, therefore, in the design of the stack it is important to consider the residence time. Residence time of the flowing gases is important, because scrap will be heated through the heat transfer between the flowing gas and the stagnant scrap, which are kept on the water cooled bars, as you have seen in the figure. Now, since the gases are flowing at a particular speed, in order to preheat the scrap at a maximum temperature, it is important that the residence time of the gas should be maximized. So, in this connection, for example, residence time that will be equal to diameter of the stack upon flow velocity of the gas, upon flow velocity of gas. The flow velocity of gas is low, the residence time will be high. The flow velocity is high, residence time will be low for a particular diameter of the stack or preheater. Now, what is important here? That one is to optimize between the dimension of the preheater or stack and the rate at which gas is exiting from the furnace, because ultimately rate of production of gas in the furnace, it must match with the rate of gas finally exiting through a recuperator. If the rate of exit of the gas through the recuperator is small, then rate of production, then the gas will be accumulated in the reactor, which is not good. In opposite situation, it is also not good because the gases are flowing very fast. So, in one case it will not heat to the desired temperature, in another case the gas will accumulate in the chamber, which is also not good. So, what is important? One has to have an optimized design of the preheater or of the stack in terms of dimension, for example, diameter, which must match with the flow velocity of the gas, because both will decide what is the residence time, and eventually this residence time will determine what is the preheat temperature. In fact, the waste gases in the preheater, it enters at around 1300 to 1350 degrees Celsius. The scrap is heated up to 800 degrees Celsius. In fact, these small globules which are shown as the scrap up to 800 degrees Celsius. Around 800 degrees Celsius, the gases passes into the recuperator. This is what the important part in the stack design, among others also, because you have to have a tight sealing between the furnace and the stack, otherwise leakage will be there. So, these are all the engineering construction of the entire assembly. Another important thing that has to be optimized is size of scrap. Too large size, too big size, too small size, both will not be good. Too small size, it is difficult to accommodate in the stack. Too large size, they will not be heated up to the temperature. So, that also is to be decided. Third important part of the EOF is the recuperator, as shown in this particular figure. So, you notice in this particular figure, this is the whole aspect is the recuperator. In the recuperator, what is happening? The exit gas from the stack is entering into the recuperator at around 800 degrees Celsius, and the exit gas is discharging to a temperature around 350 degrees Celsius, which can vary. That depends what is the length of the preheater, what is the length of the recuperator for a particular cross sectional area of the recuperator. So, in the recuperator, oxygen is entering from top and preheated oxygen is entering into the furnace. So, in fact, the design of the recuperator is equally important, because the gases which are entering into the recuperator at 800 degrees Celsius, it is important that you should be able to extract as much amount of heat as possible, so that the discharge temperature of the exit gas is very low. So, for the design of the recuperator, what is important? The length of recuperator for a given cross section area. For a given cross section area. Again, the oxygen is heated through the walls of the recuperator. When the hot gases flows through the recuperator, the walls of the recuperator are heated and oxygen flows, and through the heat transfer from the wall to the oxygen, flowing oxygen, the heating of or preheating of oxygen occurs. Now, remember, the oxygen is entering at 25 degrees Celsius. So, at the most it could be heated up to 200 or 300 degrees Celsius, that of course designed on the length of the recuperator when a cross sectional area is being decided. So, in the design of the recuperator, and this recuperator is works for example in the counter current mode. This counter current mode is the most efficient design of heat transfer between the flowing fluids. So, you see that there are several issues are involved in the design of an EOF, energy optimizing furnace. These furnaces are working. You also note from here that the reactants are entering at 25 degrees Celsius and the exit gas is discharging at around 300 to 350 degrees Celsius, number 1. Number 2, because of the post combustion in the furnace, you are utilizing the chemical energy of carbon monoxide, also sensible heat of the exit gases for preheating of the scrap. So, it is leading to some extent to an ecological balanced technology. Now, as regards the operation, say conventional operation is for 60% scrap, carbon is injected to take care of the heat balance, waste gases which are produced through the refining of carbon to CO, they enter into the stack at 1300 degrees Celsius, preheats the scrap. After that, the gases at 800 or 850, whatever the temperature, it enters into the recuperator, discharges around 300 degrees Celsius, and then the preheated oxygen enters into the furnace. This is what, for example, when you use 60% hot metal and somewhat 40% scrap. Now, it is also possible to operate the furnace with 100% scrap. It is also possible to operate the furnace with 100% scrap. Now, for 100% scrap, what is important? A liquid heel is left in the furnace from the previous heat in proportion which depends on the scrap proportion. Higher is the scrap proportion, higher is the amount of heel. Now, the operation in this case starts with the injection of carbon naturally, because C plus O is equal to CO. As you have learned from the steel making fundamentals, it is the principal heat producing reaction. So, the heat will be produced, accordingly one has to inject carbon, because scrap does not have much of the carbon. So, the operation begins with the injection of carbon until 3% carbon in the liquid heel has been achieved, preheated scrap is charged and refining commences thereafter. So, oxygen for refining and post combustion, they begin simultaneously. In both operations slag forms, rest of the practice is exactly similar. Slag will form, slag will be foamy in nature because of the carbon monoxide bubble and so on. Refractory consumption is kept within the limits by using water cooled panels and scrap supporting bars. Now, some of the important features, this is a sort of a combined blowing technique in which oxygen is submerged to the bath as well as from the top Second important feature, it utilizes the sensible heat of off gases. Third, this method is flexible in terms of use of hot metal and scrap. Liquid steel with low level of phosphorus and sulfur is possible to produce, low noise level, and an average of 42 heats per day is possible. And another important feature is that you are using 100% scrap with no electrical energy. That is also the important part of this. Steel quality aspects. Due to continuous slag flushing, if you adopt that practice, a sulfur content of very low value is possible. Similarly, phosphorus content is also of very low value is possible. That means steel quality is in general very good. Now, the basic characteristics, that is what are the availables about EOF furnace, the basic characteristics. These furnaces are available of the capacity 30 to 40 tons or 60 to 80 tons or 100 to 120 tons. Hearth surface, the dimension varies from 6.6 to 22 square meter. Shell diameter around 5.3 to 7.5 meter. Total height of an EAF unit, which consists of furnace to the stack and recuperator, it is around 17 meter to 25 meter. Of course, that depends on the capacity of the furnace. Tilting tapping angle is around 8 degree. Some of the advantages which are claimed. Some of the advantages which are claimed for this process is that first, as you noted, flexibility in terms of use of metallic charge. Second, no need of electrical energy. As you noted, even for 100% scrap operation, you do not need any electrical energy. Third, high productivity. Then, if you make the proportions 60% hot metal or you increase the proportion of hot metal, then naturally you have low tramp elements. In case of increasing proportion of hot metal, but if you use large amount of scrap, then the scrap contains tramp element, it will all enter into steel. As claimed, low inclusions and slag free tapping is also possible. Energy saving is obtained due to post combustion, which is of the order of 95%, is very high post combustion. Scrap preheating, because scrap is being preheated up to 850 degrees Celsius, and high operational flexibility. Now, consumption of some raw materials. Consumption of some raw materials. Hot metal 778 kilogram per ton, say around 70%. Then pig iron and scrap, that is around 330 kg per ton, which is say around 30%. Lime 45 kg per ton. Oxygen, which is important, 50 to 70 cubic meter per ton. Then fuel that is also use 5 to 10 megacalorie per ton. Tapping temperature is 1700 degrees Celsius without ladle furnace, and it is 1650 degrees Celsius with ladle furnace. So, this is about the energy optimizing furnace. Now, another important emerging technology is Konark. Konark, in fact, it is a combination of converter and electric arc furnace. Now, you recall in 60s and 70s there was a discussion about the advantages and disadvantages of top blown converter and bottom blown converters. Through the discussion, a technology has evolved which is top and bottom blowing, and this particular technology after 70 it has diffused the steel industry. Past few years a discussion again started about the converter steel making and electric arc furnace. There are advantages of converter steel making, it can use hot metal. There are advantages of electric arc furnace which can use scrap. An idea is there, why not to combine both the features? That way the process which will be developed after combining both the features, say converter and electric arc furnace, that will be very flexible in terms of use of raw materials, for example pig iron, scrap, hot metal, DRI and iron carbide. So, the whole idea is that because of the fluctuating steel market, because of the fluctuating availability of scrap and hot metal, it is imperative to have a process which is highly flexible in terms of use of the raw material, and at the same time it should be ecological balance, at the same time it should use less amount of electrical energy, and that has given birth to the so called process which is called Konark, which is converter and a combination of converter and electric arc furnace. So, it is in fact a twin shell concept. It is in fact a twin shell concept. One shell is operated in electric arc furnace mode and another is operated in the oxygen lance mode. In the Konark process, I have nothing to say much. I have already told about the converter steel making, already I have said about the electric arc furnace. The only thing, it has to be combined. So, it is all a technological that has to be developed or that is already developed. In India, ispat industry in Dolvi, Maharashtra has been integrated with ispat converter and arc furnace. Now, this particular combination made ispat industry to use flexibility of raw material. Another company in India which is the Bhushan Steel and Strips Limited, Bhushan Steel and Strips Limited have also used Konark process for steel making. Around the world there are around 12 units which are working on the Konark process. Now, further if we think of the emerging developments, then most of the energy developments in the future will be decided by the choice of energy, whether coal and oxygen on one hand and electricity and electrode on the other hand. So, these two sources of energy that will decide the future of steel making. So, the next topic is steel making refractory. Now, by now you must be very conversant that steel making practice cannot be successful unless high quality refractories are available. With the development of so many modern gadgets, refractory development has also to go side by side, because without refractory, the developments in steel making technology is very difficult. Typical example, you want to employ post combustion of CO to CO2 and H2 to H2O in the freeboard of the BOF or electric arc furnace generates a very high temperature. In order to sustain that high temperature, refractory is a very important component. In fact, if I may say, refractory is the heart of steel making. Coupled with the fact that now the customers have become more choosy, they also want a high quality product. So, the diversification on steel products and their quality requirement in recent years increased the demand for high quality refractory materials. So, refractory is a very important component in all emerging trends. Just now we have seen Konark process, a combination of converter and electric arc furnace. You have to join both of them, you require a refractory. Metal is flowing at a very high speed. In EOF furnace, you have seen stack is connected with the furnace and is connected with the recuperator. You require a very high quality refractory. So, refractory is a heart of all steel making developments also in future to come. What is a refractory? What is a refractory? Refractory is a material which can sustain high temperature without fusing. For example, fire clay, alumina, magnesite, chrome magnesite and dolomite. Refractory materials are produced to meet the specific demand of the steel industry. Mind you, refractory materials are produced from the naturally occurring raw materials. They do not occur as such in the nature, but the raw materials occur in the nature, and from that the refractory material of the required and desired quality are produced so that it can match with the requirement during conversion of hot metal to steel. Mind you, there are very diversified requirements in the steel making technology. These requirements not only in the steel making technologies, but also cement industry, glass making industry, ceramic industry, all require refractories. But steel industry is the major consumer of refractory. I can say very boldly, if there is no steel industry, the refractory probably will not be required of that high quality. Why do you require a refractory? For two reasons. First, to minimize heat losses. To minimize heat losses, because you cannot use a steel shell. If you use the steel shell, all the heat which is produced inside the reactor formed by the steel shell will be lost. The reactants and product may react, so it is not possible to use a steel shell. Therefore, to minimize the heat losses, refractory is required. For this, thermal conductivity of the material is important. Another important part why you want to use refractory, to allow thermal energy dependent, conversion of reactants into products. Now, again metallic vessels are not suitable, because in steel making we handle phases like liquid steel, which contains iron, carbon, silicon, phosphorus and so on. A metallic shell will not be suitable. We also handle phases like liquid slag, which is an oxidic mixture of inorganic compounds. We also handle gases. Which gases? Could be carbon monoxide, carbon dioxide and nitrogen. These phases are in contact and constantly in motion. The flow is highly turbulent. The gases are also moving with certain speeds. Among this, CO is reducing, CO2 is oxidizing and nitrogen is inert. So, because of the handling of phases, because of the presence of phases for a long time means for the duration which is required for conversion of hot metal to steel. For that particular time you need a material which can sustain the temperature, chemical reactivity and so on of the hot metal, slag and gases. Now, let us see what are the types of refractory materials are available. Types of refractory material. As such, we have oxidic, special refractory material. Among the oxidic, we have three type of oxidic material. One is acidic. In acidic, SiO2 is the main component. For example, fire clay, quartz, ganister, and these acidic refractory material cannot be used in contact with a slag which is basic in nature. Now, remember, slag is also a mixture of these oxides, if you remember the lecture on slag making. If you use acid refractory in contact with the basic material, then there will be reaction will take place. So, these are not useful under basic. The acidic material can only be used under acidic condition. Another, we have basic refractory, and basic refractory, for example, magnesite, your dolomite, you have MgO, C, and there are further type of basic refractories. Now, these basic refractories cannot be used in acidic environment. They can be used only under basic environment. Third, neutral refractory. Neutral refractory, for example, chromite, carbon or mullite, they are neutral refractory. These refractories can be used either under acidic environment as well as under basic environment, depending on the requirement. Then under the special category, one we have silicon carbide refractory. Then we have cermets. Mind you, they are special and high quality refractory. And third is the Silon, SiAlon, that is silicon, aluminum, oxygen and nitrogen. Cermets is a combination of a metal or an alloy and non-metal. For example, oxide, nitride and boride and so on. Now, these cermets, these refractories, they have a very low thermal shock resistance and high strength at high temperature. The cermets, they are produced by processing of powders of ceramic phase and metallic phase, and these cermet refractories, they are very hard and strong. Now, something about the silicon carbide refractory. Silicon carbide refractory, they have, say, carbon is greater than 85%. Some of the properties, the silicon carbide refractory have high thermal conductivity, and high refractoriness. They decompose around 2200 degrees Celsius, but does not melt. High thermal spalling resistance, excellent mechanical properties and a lightweight. Silon refractory, SiAlon. These refractories are a solid solution of alumina in silicon nitride. Hot pressing of this mixture is done at 18 to 30 megapascal pressure and 1700 to 1760 degrees Celsius in graphite molds to get a low porosity dense product. Certain properties of Silon refractories, mind you, Silon refractories are excellent refractories for very critical applications. First advantage of Silon refractory is good resistance to oxidation, good resistance to oxidation and action of molten metals like copper, aluminum, iron and steel. That is one of the very important property that these Silon refractory has. They are highly resistant against the action of these liquid metals. Second important property that these Silon refractory have is the refractories are not affected by H2SO4 or HCl, borax and alkalis. But the only problem with this refractory, they are very expensive to produce these refractories. In the next lecture, we will be seeing the further details of the oxidic refractories, the manufacturing of these refractories and some important properties.